Welcome to Configuring ScreenOS Firewalls. This is the session on Layer 3 operations. So in this session, we'll be discussing how your firewall behaves as a router and the basic routing functions that are available in ScreenOS. So the objectives for this chapter are to be able to understand and explain the need for routing, to be able to explain and understand the virtual router architecture and how that gets implemented inside of ScreenOS, to configure static routing. Static routing protocols will be covered in this lesson, where dynamic protocols are covered in the advanced courses. We will go over the loopback address and how to configure that on the ScreenOS device. And you will learn about the difference between interface modes NAT and route. There is a ability to do NAT on an interface basis as opposed to a policy basis. This is considered a legacy feature, and it's preferred that you use other methods of NAT, but it is still available in circumstances, and we'll go over those. And you will learn how to do that configuration for NAT versus route mode, and we will learn how to verify and do basic troubleshooting in Layer 3 on the ScreenOS device itself. So with that, we begin with the first section of our agenda, which is routing, and talk about how routing is necessary and the implementation in ScreenOS. So here we have a basic 2-office multiple LAN situation that we'll use as our example for routing mode. We have a headquarters that is connected to the internet and using a net screen, and we have a regional office connected to an SSG-20. They have an IPsec VPN tunnel that connects between them, and you can see listed on the diagram are the IP addresses in use by the zones and subnets at the two offices. So as a result of having 3 zones and subnets in the regional office, we have connected routes on Ethernet 01, Ethernet 02, and Ethernet 03 at the regional office. Now, these interfaces then are configured with these IP addresses, and just by the virtue of configuring an IP address on an interface, your ScreenOS device will create a route for those networks that are connected to the device. So it will create a host route for the interface itself, and it will create a network route pointing to that interface, knowing that that interface is that subnet is available on that interface. So there is no need for you to do anything other than configure the IP address on the interface, and then these connected routes will show up in the routing table. Now, on the remote site from the SSG-20, you can see that the subnet is 10.21.0/24. And we would reach that over that IPsec VPN tunnel, and the interface there on Ethernet 01 on the net screen 5400 will be configured to 10.21.1 in this case. So this route 10.21.0/24 out interface Ethernet 00, and with a destination of 10.21.1 across that tunnel, becomes a static route that we had to create in order to be able to reach the remote network from the headquarters network from the regional office network. And then finally, in order for internet access to occur, we would need a default route to be created. The default routes are created by using 0.0.0.0/0, and they would be directed to the interface pointed to the internet, and then that IP address will be the default gateway address that your internet-facing interface is connected to. And so as you get to the bottom of your routing table, if the destination address is not on any of the specific addresses in your routing table, we will pass it to the next device we are created to by default, our default route. So this is the review of what you already know from your networking background. This is how this ScreenOS handles it. Connected networks are automatically created. Remote networks must be created by either static routes or a dynamic routing protocol, and your default route has to be created, and your default route on NetScreen will be created as a route. It's not going to be created as a default gateway property on the interfaces. Okay, so moving from the diagram over to ScreenOS itself, this is how a basic layer 3 network might look in a single virtual router operation on a ScreenOS. So in this diagram, we have a single VR, a single virtual router. We have two interfaces configured on our ScreenOS device. So the box that says single VR is our ScreenOS device. The other four routers on here are external routers that are available as destinations for ScreenOS. So you can see there's two subnets there. There at the top we have 10.10.20. So our ScreenOS device is at .1, and our other two routers are at .2 and .3. So these two routers have an interface on the same subnet with ScreenOS Ethernet 0/1. On the bottom, Ethernet 0/2 is in the 10.10.10 subnet, along with these other two routers. So our Ethernet 0/2 is at 10.10.10.1, and our two routers are at 10.10.10.2 and 10.10.10.3. So we have three devices in each of these two subnets that are connected to each other. And then behind each of those routers, we have additional subnets are available. So we have the 10.10.3.0, 10.10.4.0, 10.10.1.0, and 10.10.2.0 behind each of these four routers. So let's take a look at how the routing table will look on a single VR in this type of network scenario. So here's our routing table. There's several things to notice when you look at the routing table and get route on the ScreenOS device. In the very first column, you see in this case there's an asterisk. The asterisk is indicating in ScreenOS that a route is up and active. So you may have multiple routes to a particular subnet, or you may have a gateway that is not reachable, or an interface that is down. If an interface is down, the route will fade and the asterisk will go away. If the gateway is not visible to ScreenOS, the route will fade and go away. If it's a duplicate route to something else in the routing table, only one of those routes can be active, and it will use the preference and metric to determine which of the two routes should remain active. If the two routes have the same preference and metric, then they will both remain active. So you can have two active routes that are exactly the same, and then the ScreenOS will round robin sending traffic to them. So the first column, asterisk, is telling us whether or not the route is active. The second column is simply an ID number. This is just a way for ScreenOS to identify the route. It has nothing to do with the route's preference or metric. This is just the identifying number, unique identifying number for the route in the route table. The next column is, of course, the network itself. So this will be listed in the routing table in CIDR format. 10.10.21/32, 10.10.20/24, just the network that we're talking about. Next, we will have the interface that the network is reachable over. So here we can see that the first two routes, our ScreenOS device is configured at 10.10.20.1. So the first two routes here are the automatically created networks for the interface 10.10.21/32 and the subnet 10.10.0/24 for Ethernet 0/1. They have no gateway, and you can see that because they're on the device itself. And then that brings us to the next column. We have the letters H and C. H for host, because it's a /32, and C for connected, meaning it is a subnet that is directly connected to this device. So connected routes that are automatically created have the lowest preference and metric numbers. Lower preference means we're going to use them first. So 0 and 0, nothing gets routed before a connected interface IP or a connected network to the device. So preference and metric are what gets used to determine who wins or who might get faded in a route. Metric is evaluated first, and then preference. And then the final column is telling us which virtual system that this route belongs to. In this case, everything's in the root vsys. There's only one vsys and one VR in our system for this operation. Okay, so that's what all the columns are, and that's our connected and our host route for the interface itself. The next two routes, Route ID 3 and Route ID 4, you can see are static routes. That's the S in the column indicating the kind of route it is. Those do have a gateway and an interface. And in this case, the gateway is going to be the IP address of the router that services those subnets. So these are from the top of the diagram. We have those two networks, 10.10.3.0.24 and 10.10.4.0.24, that are on the top part of our diagram. They can be reached through the routers at 10.10.22 and 10.10.23, which are connected to Ethernet 0/1. And then the default metric and preference for static routes is going to be a metric of 1 and a preference of 20. When you create the static routes, which we'll go over a little later, you can manually assign these values if you need to be able to establish preferences to routes in multiple paths. Or you can make them the same if you want them to round robin and use both paths. So the remainder of the table is the same as those first four. We see our two connected routes for the host and the connected network on Ethernet 02, and we see the two subnets on the bottom that are behind our routers at 10.10.2 and 10.10.3. So this is what happens on a simple network, single virtual router, and the routing table that would be created for using static routes to reach each of these devices. Okay, so now we're going to take the same network and divide it into two virtual routers. In this case, the top interface, Ethernet 01, is going to belong to the Trust virtual router, Trust VR, and the bottom interface, Ethernet 02, is going to belong to the Untrust VR. You'll notice everything else in the network is the same. We still have the same 4 subnets serviced by the same 4 routers and the routers are assigned to the same 4 IP addresses. But what we've changed is only in our ScreenOS device. So in our ScreenOS device, we now have 2 virtual routers servicing these same 4 subnets. The routing table then will look like this. You'll notice it's organized into the 2 VRs. They have each virtual router has its own independent routing table. The routing tables of those VRs are not shared with each other. So when a packet arrives on the Trust VR is only going to reference route entries in that top table. Likewise for the bottom. If a packet arrives in the Untrust VR, it can only reference the routes that are in its own routing table. But you'll notice that the route IDs are unique across all of the 2 VRs. They are unique across all of them because both of these VRs belong to the same vSys. So within the vSys, the numbering is unique. But the 2 virtual routers will not reference each other's routing table. So the first thing you'll notice here is that in this simple scenario, each virtual router only has access then to the devices that are connected to its own interface. We did not create any routes in the Untrust VR to be able to reach the Trust VR. In this scenario, as it's configured here, there is no traffic passing between the Trust VR and the Untrust VR. They don't have routes created to each other. So when you use virtual routers, they literally are as if it's separate boxes. And if you want them to be able to route and talk to each other, you do have to create the routes so that they can see each other. ScreenOS does support dynamic routing protocols. They have support for RIP, OSPF, and BGP. These can be configured with a full range of protocol support for these protocols, but the operation and configuration of dynamic routing is part of the advanced ScreenOS course, so we won't be going over it here, but the devices do support these dynamic routing protocols. Okay, so now we've looked at the basic routing and what static routing is going to look like in the virtual router system of the ScreenOS. Let's take a look at how the configuration gets done. So here's our basic network for the configuration review. We have a SSG 550 in the middle. We have 2 zones, the Trust zone on the left, which is our internal network at 10.1.10.5, and we have our Untrust zone on the right. There are 2 Ethernet interfaces, 00 and 01, configured on the ScreenOS device, and there is one router to either side of the ScreenOS, one in the untrust and one in the trust. And then we have our sample web server at 200.555. So this is our sample network for the configuration exercise here. So we're going to configure layer 3 on this device. We need to review quickly that we have a virtual router which is containing a single virtual router which contains all of these devices. Your zone, either trust or untrust, is going to belong just to that virtual router. And then your interface is owned, assigned to and owned by the zone. So the interfaces belong to the zones and the zones belong to the virtual routers. This is our strict hierarchy that ScreenOS has. So if we're going to configure layer 3, the first thing we need to create then is the zones. The ScreenOS's devices come with the virtual router already created. You don't need to create that unless you need additional ones. We will assign then the interface to that zone that we're going to use, and then we will assign the IP address necessary to the interface, and then we will create the static routes that are necessary to reach the networks on our network. So step 1, we're going to create the zone. Zone configuration on the command line is the set command, set zone name, and then you give it the name. So the capital name here would be trust, untrust, which are the defaults already created on a branch device, or red, blue, green, accounting, management, whatever name you want to give the zone you're creating. On the web interface, this is under Network Zones and hitting the New button, and then you'll be presented with the form to fill out, giving it the name, assigning it to the virtual router. Next, we need to assign our interface to the zone. So in the zone configuration, we are going to say set interface Ethernet 0/0 zone untrust to match the setup on our diagram. We've now put Ethernet 0/0 into the untrust zone. And in the web, we would go to Network Interfaces, edit the interface that we're going to configure, and then we would select the zone from the pull-down list and click OK. Now that we have our interface in the zone, we can assign an IP address to it. So IP configuration, also with set interface Ethernet 0/0 IP 1.1.1.1/28. So that will put the IP address 1.1.1.1 onto Ethernet 0/0 in that subnet facing our ISP router. In the web, this is on Network Interfaces Edit. The interface 0, the edit button next to interface Ethernet 0/0. And this portion of the web interface, you can place then the IP address, selecting static IP, filling it out, and in this case we're going to enable management on it. Next, we're going to talk about bridge groups. Bridge groups are a special interface type. Bridge groups allow you to create multiple interfaces into the same subnet on the ScreenOS device itself. So you can take several interfaces and put them together into a bridge domain. They're called bridge groups because this is an Ethernet bridge domain. This essentially creates a logical layer 2 switch inside the ScreenOS device. This can contain multiple wired interfaces that are physically on the device or on the add-in cards of the device, placing them all together. You can add wireless interfaces to the bridge group. If the device has wireless, obviously, and then they will be on the same subnet as those wired interfaces. And this is what a bridge group will look like when it's displayed in the web interface. So here we have B group 0 and B group 1. Notice the IP addresses are assigned to the bridge group, not to the interfaces. So the bridge group is a special type of interface that is higher than the physical interfaces. The physical and wireless interfaces belong to the bridge group, and then the IP address is assigned at the bridge group level. So here we have the zones that are assigned also at the bridge group level, and these become then a layer 3 interface that includes multiple interfaces below it, and they can be either physical, multiple physical, wireless, or a combination of those. These can be handy for, bridging across multiple external switches or other devices and placing them all together in the device. It puts this mini switch inside your ScreenOS device. So to configure a bridge group, we would use these commands. You'll notice that this is the number 1 that's after the B group there. Displaying a little funny. It's not an I, it's the number 1. So set interface B group 1 zone trust, set interface B group 1 port Ethernet 0/1. ETH 0/1 is now a part of that B group, and wireless 0/2 is now a part of that B group, and then we set the IP address. So you'll notice the zone and the IP commands are the same as any other interface. Instead of set interface Ethernet 0/0, we're doing set interface B group 1, B group 2, B group 0. On the web interface, you would go to network interfaces, edit the B group that you want to configure, and then on the bind port tab is where you show which interfaces will belong to that group. So you can see all the memberships of B group 0 and B group 1 that we saw in the previous slide, and by changing the checkboxes you can rearrange the interfaces that belong to this particular bridge group. Okay, static routes. To create the static routes that we need for our network, we have these commands. Notice here there's a hierarchy of virtual router VR. Set VR, the name of the VR, VR-trust, route 10.1.10.0/24, interface Ethernet 0/1, gateway 10.1.1.254. So these are all the elements we need for the static route. What virtual router are we putting the static route in? What network is the static route for? What interface can we reach that network through? And then what is the gateway device that will pass on the traffic to that network? So in our previous diagram, we saw the router interface was 10.1.1.254, and the subnet behind that router was 10.1.10.0. So very straightforward, just all those elements in that order. In the web interface, this is available under Network Routing, Destination Routing. So these are routing based on destination. You fill in the network in the top part. You select gateway, interface, and the gateway IP address. In ScreenOS 6.3, you can also add a description to the routes on the bottom part of this, so that when you create static routes, you can put a little human readable label on them. And you can see on the bottom of this form here, you can change the metric and the preference. If you don't do anything, as this command is written on the CLI, the metric and preference will be set to these, 1 and 20. If you keep typing, you can manually assign a metric and a preference in this same route command. So very straightforward. We've now created the zone. We've assigned the interface to the zone. We've put an IP address on the interface. We've configured the B group for our trust interface, and now we've added a static route to our internal network. Those steps are all that's necessary to configure static routing on that single internal network step. So let's take a look at once layer 3 is configured, how do we see what these settings are and verify that a configuration is in place. To look at the interfaces on the command line, we can use the get interface. Notice if you type enough of interface to make it unique in the ScreenOS command, in this case INT, it will just return a list of the interfaces on the device. So this shows us that this particular device that we did a get interface on doesn't have any of the IP addresses configured on anything except this bridge group 0. And that's been assigned to the trust zone, and it has an IP address of 192.168.5.1. So we can use get interface to confirm what zone assignments and IP addresses have been configured on the interfaces before we start. In the web, you look this under the interfaces area. So when you go to network interfaces, on some of the branch ones, there's also a list button. You get a list then of the interfaces that are on the device and what their current configuration is. To take a look at what's in the static routes in the routing table on the CLI, we're going to use the keyword route. So get route will bring back the routing table on the device. So this is a sample routing table for the same device we just saw in the previous slide. It has that B group 0 at 192.168.5.1. And it does give you that nice little description at the top on what the meaning of where the routes are coming from are. In the web, you would look under network routing destination, and when you pick that, it pulls back a tabled version of the routing table on the web browser. So get route and network routing destination will show you the routing table on the device. If we want to verify that our routing is working, we can use the get route command on the device to see what the routing table is. And then in this case, we can say if we want to go from the ScreenOS to our internal computer, 10.1.10.5, this will show us the specific path that will be taken to reach that network. So get route IP 10.1.10.5 says it will use this route in our routing table, 10.1.10.0.24, and it will send it to the gateway of 10.1.1.254. So if you're having routing issues, this can be a handy way to see what the ScreenOS is doing. If you can't reach a destination, or you want to know if a route to a destination already exists, you just type in get route IP and the IP address, and ScreenOS will say which direction and which route it's going to use to forward traffic to that address. The ping command is available on ScreenOS. works pretty much the same as everywhere, just ping in the address. By default, when you hit ping in an address, it'll send 5 ping requests, and then it'll return whether it's a success or failure and how many. So in this case, 100% returned of 505 with the round trip time, showing you the minimum, the average, and the maximum on all 5 of those attempts. If you want to customize the ping command, you can either enter these parameters that we show here manually, or if you just type the keyword ping, it'll give you a prompt for every one of them. So you can prompt you then for the address you're going to go to, how many pings you're going to send, the size of the datagram if you want to be testing your MTUs or other nature, or you want to see if the data packet size is affecting the transit times. You can change the datagram size, you can change the timeout, and you can specify a source interface that the ping will be sent from. By default, when you just type ping, the ping will be sent from the lowest numbered interface on the device, or the loopback address if one is configured. Otherwise, you can specify ping from a certain interface in order to trace network problems. Trace route standard command is also available. It's trace-route, then the IP address, and it'll return back the path that it takes to get to that device. And you can also use the from interface from this. So if you're doing network tracing and you need to know from a specific interface, it can do that. You'll notice the first one defaulted to the lowest numbered interface, Ethernet 00, and the second one we did it from Ethernet 01, showing the path that it will take to get there from that interface. Okay, routing interdependencies. Let's take a look at how host A is going to communicate with host D. So A is our 10.1.10.5 in our internal network, and host D is our web server 20.5.5.5 on the internet. So when the traffic first gets generated on the computer 10.1.10.5, it's going to be received by this router. So this router will be sending that traffic to its default route at 10.1.1.1, which is the interface of the SSG5. So the only thing it knows about is a default route to the SSG550 and its connected network. So since 200.5.5.5 is not a connected network, it's going to use the default route, and then the SSG550 is going to process this. The SSG, the router on the other side of the SSG550 is going to then receive this traffic from the SSG550, because the only thing the SSG550 has connected is to the internal network, and it's going to use its default route. Okay, we have several debug facilities for trying to follow traffic problems in ScreenOS. These are utilities for internal operations in order to see what's happening at various levels of protocol. They are available for all the common types of traffic you may need to troubleshoot. Debug Flow Basic is probably the one you'll use the most. This allows you to take a look at a flow of traffic from a destination to a source, and how it's handled on the flow through the ScreenOS. Debug NAT will allow you to look specifically at NAT operations. Debug ARP is looking at the layer 2 ARP operations and how those tables are handled. Debug DHCP is available for troubleshooting DHCP requests that aren't completing their whole negotiation. We have Debug IC Detail for Internet Key Exchange and VPN operations. And we have Debug PKI for certificate exchanges that are not working as you expected. So all of these debug facilities are available to take a look at the specific transactions that are occurring on the device to help debug what's going on. By default, the output of any of these debug operations is going to go to a buffer that's stored on the device. This can be redirected to the console so you can see it happening live as your traffic is occurring. Or you can allow it to go to the buffer and then stop it and read the contents of the buffer after. It's generally recommended that you go to the buffer and then read the content. Running the debug to the console can be, depending on the traffic you're running, can be CPU intensive. So what is the buffer and how do we set it up? Get DB info will tell you the current configured size, how much data can be stored in the buffer. You can allocate different sizes. It can be helpful to make this small so that you don't have tons of stuff to go through. Just capture a little bit of traffic and have that to go. Get DB stream is how we look at what's in the buffer on the console. So get DB stream will pull the current contents of the buffer and view them, or you can redirect them to a file or a TFTP server. Set DB size is how you allocate the size of that buffer, how much traffic you're going to capture before it gets full. And then clear DB is how we empty it out to get ready for the next round of capturing. So that's how we handle the buffer in order to use it. You would see what's in it, maybe clear it out, set a size for it and clear it out, and then you would run your traffic, and then you'd use get DB stream to see what is in the buffer itself, so you can do how your traffic was handled. Okay, troubleshooting tools. The output of our debugs goes to the buffer by default. We do have an option to send this to the console, as we mentioned earlier, and these are used, are set or unset using the keyword debuf, D-B-U-F. So get console will show you what the current setting is. You'll see there highlighted debug buffer. So the current setting is the default, meaning that it'll go to the buffer. If you unset console debuff, that will change the setting to be debugging directly to the console. So as your traffic runs, the buffer will display on the console. You would reverse that by simply saying set console debuff, and that would put it back to that first setting, debug going to the buffer. So that's how you would toggle that if you do want to see the output on the console. The way we capture traffic into this is by using a flow filter. The flow filters allow you to set IP addresses, protocol numbers, or port numbers, either source or destination, or using AND to capture information. The command for doing this on the command line is set F filter for flow filter. You can see here the options you can set with the question mark command here. You would have the destination IP address, the destination port, the IP protocol, the source IP address, or the source port. So these are all configurable in a flow filter in order to narrow down what you actually put into that debug buffer. So how do we set this up? You can narrow down very narrowly. You can use logical AND conditions where both of the source and the IP address have to match, for example, in order to do this. Logical ANDs. In order to do this, you enter both conditions on the same line of the flow filter you create. By putting them on the same line, both conditions have to be true before the traffic is put into the information about the traffic is put into the buffer. You can set up logical OR conditions if you need to cast a wider net and pull in multiple things to see what's happening on the device. To do this, you simply set multiple filters. When you set multiple filters, anything matching any of the filters will go to the buffer, while same line, everything has to be met. So this is what that looks like. Here's 3 filters being set on the ScreenOS device. This is a logical AND. All 3 of these conditions have to be met before the device will capture that traffic to the buffer. And these are logical ORs. Any traffic matching any of those 3 conditions will be sent to the buffer. If you want to see what filters are currently active and created, we would use the get F filter to show the currently configured ones. So there's our 3 filters that we had created in the previous slide. IDs 0, 1, and 2. In order to remove a filter, because you need to either narrow this some more or otherwise control it, you would unset and then the filter number. So this will remove filter number 1, and as you can see when we get the filters now, the old filter number 1 with a source IP of 10.1.1.1 is gone, and the old filter number 2 is now filter number 1, destination port 80. You remember this from the previous session? Well, this is our ScreenOS packet flow. So when you're setting up flow filters, it's important that you remember how the packets are going through the ScreenOS device. First thing that happens is this sanity check. You know, is it a valid packet? Is it something we should process, or does it have some anomaly in it that we want to discard? The second check is it an existing session? Match it to the existing session and perform the actions that are saved for that session, or it's not an existing session and we have to figure out what to do with it. The destination lookup and any NAT involved then allows us to see if the destination address is reachable. If it's not reachable, we don't even want to deal with it. If it is reachable, then we use the destination address and the source address to determine what the entrance zone, exit zone are, and do a policy lookup. If it's okay by policy, we can do our ARP query and perform the policy action and add the session to the table. So this is the review then of our packet flow in ScreenOS. Let's see what these will look like when we capture some traffic in a debug session. So what's the procedure for using debug? The steps are to take a look at what filters are already created. So we're going to use the get F filter to see if there's filters created. If there's filters already there and they're what we want, great. If they're not, we have to remove them. Then we're going to set the filters we need to capture the traffic we're troubleshooting. So we'll set up our logical AND or OR conditions, create the filters. Then we enable Debug Flow Basic to be able to grab the flow. We will clear the current buffer so that there's nothing in it, and we can capture our traffic. We will then send the specific traffic that matches the conditions we want to see. So we'll set up that ping command, open that web page, do whatever it is that we're going to do to generate the traffic that we want to observe. We then do undebug all, or hit the escape key to stop the traffic capturing. And then we're going to use the getDBStream command to pull the data we've just captured out of the buffer. And then when we're completely finished with the troubleshooting session, we would unset all the flow filters that we created in the device. So these are the basic steps for the debug procedure. These are listed on that command reference card for the lesson that you can download from the class site. So let's see what some output will look like from that. Here we have a basic untrust situation with a computer in the trust zone 192.168.1.111 going to a computer in the untrust zone 72.30.2.43. So we would do our getF filter, and there's nothing there, so we're good. We clear the DB. We set up debug flow basic. We will create our flow filter. We will capture traffic from a source IP of 192.168.1.111 with a destination IP of 72.30.2.43. We see that the filter has been added. We turn on debug flow basic, clear the DB. We send the traffic, and then after the traffic we use undebug all, and then we'll hit getDBStream. So those are all the steps listed on the previous slide, and this captures then the traffic that we were sending from the left to the right, the trust to the untrust zone on these two IP addresses. When we do getDBStream, we're going to get some output. So what does this output look like? Here's the start of this this output from the base. So let's walk through it. Remembering from your packet flow, you'll see right here is that first step. The packet has passed the sanity check. So the packet's arrived and it's passed the sanity check. We see here that it did not have a session, so no session was found. And then here it's choosing the B group 0 as the incoming NAT interface, and this is the first flow in that session. So it's looking for the route lookup, first flow in the route, and it's changing, and it's finding a route on the VR trust VR route. Cached route 781 for 72.30.2.43. It's not the first traffic that's gone to this. So therefore this destination route is valid, and it has a route out Ethernet 00 for this. So the route check has worked. Now it's going to do the policy search based on that incoming and outgoing address, and it says we are going from zone 102 to zone 1. So it's found the policy, the two zones, and it's going to do the policy search. Down here we see that the traffic is permitted by policy number 7. So this traffic is permitted traffic by policy number 7. So as you read through this, you can see each of the steps of the packet flow process is being hit here, and they're written in this shorthand so that you can see what's happening at each step along the way. So on the next slide, we're going to take a look at the remainder of this output. This is from the same session. So here's a session ID being created for the new session that was just permitted by policy. And then here is the ARP entry being made for the ARP portion of the connection to be able to send the traffic out. And then you see at the very bottom there, we're doing a port translation on our way to this, because that's obviously an internet computer address. That's a public internet address. So we translated it to the interface address on Ethernet 00 before sending it on the way. So those are the last three steps of the process that you see there. So each of these steps is found then when you do the packet capture, and this is a successful capture of traffic that was successfully went through the entire flow of packet through the device. Okay, so that was a brand new session. On an existing session, what will happen is it will go through the session rules of the table, so there'll be a lot less steps in there. It's also important to note that on the ISG and the NS series line, there are hardware flow controls available. These debug utilities are only available for flows that are happening on the CPU. So this debug flow can only see the CPU handled traffic. So if you have an ASIC device like the ISG or the NS series and you need to do this, you have to temporarily turn off hardware sessions in order to be able to see the traffic. This does affect your CPU utilization on your device and how fast traffic can be handled, obviously. So you have to be careful that you're in a situation where you're not going to overload the device when you do this. And this feature, to be able to do this, is only available in ScreenOS 6.1 and higher. So this debug flow session on the ASIC hardware flow has to be enabled in the CPU in order to be used. Okay, that was a successful traffic. What are the things you're going to see that aren't successful? You may see in the stream, instead of that final command allowed by policy, you can say pass packet. You might see packet dropped, no route. Self-explanatory. You see the route lookup failed, so you need to go back and take a look at your routing table and do that get route IP for the IP address involved, and add some routing so that the place you want to go is reachable. You might see packet dropped, denied by policy. This will happen if there's an explicit policy that is configured to deny that traffic, and it'll give you the policy number, or if no policy is configured to allow that traffic, then the global deny rule will be causing this. So obviously what you need to do here is check your policy ordering to make sure the deny is not before your allow rule, or you need to configure a new policy to allow this traffic. The policy you thought was allowing this traffic is not seeing the traffic, so it's matching something before that, or there's a problem with the parameters of the policy configured. And we'll go into policy configuration in a little more detail in another session. Another way you can troubleshoot flow is to take a look at what's actually in the session table. So if the traffic is going through the device but not operating perhaps as you expected, it may have an entry in the session table. And the session table can also tell you what traffic has actually created sessions. So we use the command get session to see the active sessions on a device. We use the command get session info to see a summary of the activity that is going on in the device. Once you've done get session and you've maybe found the session itself that you want to look at in more detail, you can use the ID number of that session to see just the information on that particular session. And finally, there's a filtering available on session. You can specify either a source IP address, SRC-IP, or a destination IP address, DST-IP, to see all of the sessions that are associated with either a source or a destination IP address. So these will allow you to see the traffic that's flowing through the device at that moment in time. So when you do pull a session, let's see what that looks like here. There's a number of elements here. At the front, we see, of course, the session ID number here. We can see what virtual system the session's in, and you can see, of course, the IP addresses associated with the source and the destination, and you can see the route that is being done, the MAC addresses that are involved. So there's a lot of detail, the policy that it's hitting in this session table entry. When you say get session info, this is the overall view you get. You know, what's the current allocated sessions? 104. What's the maximum number of sessions that this device allows? 8,000. There have been no failed allocated sessions on this device, so that means you've never hit the maximum. This could let you know you needed to get a extended license if you see a lot of allocation failures. Multicast sessions and allocation failures and free sessions in the pool. So there's lots of available sessions. So if you think you might be maxing out the capacity of your device, this get session info lets you know about these allocation failures and the current usage of your session table. For troubleshooting purposes, there is also a telnet client on the ScreenOS device itself. So on the CLI, you can telnet to another device that's reachable, of course, from the ScreenOS device. That's the same as any other telnet client. You just specify telnet and the IP address. And then you can log in to your remote switch or any other device you have. And once that session is disconnected, you'll be back again on the ScreenOS device itself. You can also specify the from interface here if you need to be able to have reachability. Okay, now we're going to talk about loopback addresses. Loopback addresses are a special object in ScreenOS. The special object does not have a physical interface. It's a virtual interface on the device that we can use to address the device, and we can also terminate things like VPN tunnels on loopback addresses and use it as a source IP address for operations on it. So there is not a physical connection ever on a loopback address. It's a virtual interface. The loopback address then can be reachable from any interface that has a route to that address. So loopback addresses are frequently used to give an IP address to a device that's independent of all the interface IP addresses. So you create a loopback address in another subnet, use that as the address of the device, as the router ID, maybe in OSPF, as the way to address the device itself, independent of the interface subnets that this is created to. In order to reach the loopback address, of course, the outside networks would have to have a route pointing to the ScreenOS device that has that loopback address. The application for this would be device management, terminating of VPNs, used as router IDs and the like for dynamic routing, neighbor relationships, and it can also be used to perform as an interface on which you perform NAT operations into and out of the device. Configuring loopback addresses. On the command line, they're an interface like any other interface, so we're going to use our set interface commands. You can have multiple loopback addresses, so set interface loopback to zone, put it in zone trust, assign it an IP address of 192.168.1.1, and we can turn management on so we can use SSH to this address to manage the device. In the web interface, this is an interface, so it's a network interfaces list. Click New Loopback IF interface, and we're presented with this. We can create a loopback.1 to loopback.10, assign it to a zone, assign an IP address to it, and enable whatever management services we want. And then here we can put the admin status to force it to be always up and available. One of the reasons you may use a loopback address for management is if you have interfaces configured on a device with an IP address, say on your internal network, if all of the interfaces have no link, if the interface with this IP address has no link, it will not be reachable. So if you wanted to use the internal interface to reach the device for management, and the device connected to that interface goes down, that interface is not reachable, it's down. Loopback interfaces can be administratively always up so that they're always reachable for management purposes. Okay, we've reached the last point of our agenda. We're going to talk about interface-based NAT. Interface-based NAT is on the interface itself, and in certain circumstances it allows you to perform NAT operations just by turning it on the interface level. So back to our sample network that we've been using, from this computer 10.1.10.5 to our server on the internet 200.5.5.5. This device is going to make a request out for this web server. So it sends out this request from its source IP to that destination IP on port 80 for web, and then its randomly assigned port by the OS is 2153. When it transits out to the internet, the device needs to be NATed. So the destination IP address and port need to stay the same because that's based on the protocol that we're going. But you'll see the source IP address gets changed to the source interface, 1.1.1.1, and then that NAT operation will randomly change that to another source port. That way, when multiple devices go across this is standard NAT with port address translation in order to reach the internet. So this can be configured as an interface parameter to do network address and port translation for internet access. There are some restrictions though. So interface-based NAT configuration is done on the interface level. Every interface is either in NAT mode or in route mode. It's an either-or situation. If the interface is placed in route mode, the interface itself will never do any translation operation. It will just pass the packets in and out and will not translate anything under any circumstances. In NAT mode, if you have a single virtual router, traffic from the trust or the DMZ to the untrust zone can be NATed automatically on the interface. If you have two virtual routers, any virtual router to the untrust virtual router can be NATed on the interface. No other circumstances will the NAT occur. So you can turn on interface NAT if you've created the zone red instead of trust. It will not perform interface-based NAT. It has to be the zone trust or DMZ for that to occur. And if you're using multiple VRs, you have to make sure the untrust VR is the virtual router connected to the interface. If you've renamed your VRs so that untrust VR doesn't exist anymore, then interface-based NAT is not going to be working. Any other circumstances besides these listed here, you have to use policy-based NAT or another NAT procedure, which will be covered in a later lesson. So the point here is that interface-based NAT, flipping from route to NAT mode on the interface, only works in a very select set of circumstances. You must be coming from the trust or the DMZ to the untrust, and all those zones have to be named those zones, or you have to be configured for the untrust virtual router connected to the internet and coming from another router to that. Okay, route mode will not perform any translation, and therefore you will manually configure your policy-based NATs or your other NAT methods that we'll cover in a later lesson in order to perform your address translation. If you're doing internal addresses, you obviously don't want to be translating in most cases. So here we have our traffic coming out again to our here, and if we're in route mode, it's going to not change that at all. And of course, as soon as this traffic hits the internet router, 10.1.10.5 is not routable on the internet, and it will be black holed by the internet facing router. In NAT mode, since we do have trust and untrust set up, we will perform the translation that we mentioned previously. The interface address will be substituted for the source IP address. The session will be maintained so that the return traffic can be found to the device. Okay, so configuring the interface mode. There are some default settings. The trust zone in a branch device will be placed in NAT mode by default when it arrives. The DMZ zone is placed in NAT mode, and the untrust zone is in route mode. So the default basic configuration with a trust B group, a DMZ interface, and an untrust interface are set up to use this interface-based NAT mode with these default names that will work with it. You can configure the internet interface mode on the command line, set interface B group 0 NAT, and set interface B group 0 route. By default, in the default configuration of a branch ScreenOS device, B group 0 is going to be the trust zone. On the web, there's a radio button to select interface mode for either NAT or route. Under network interfaces and list, and then edit the interface involved, B group or B, the B group, the Ethernet 00 or 01. In order to see what the current configuration is, you will get the interface that you want to see, get interface vgroup 0, and then that will list the mode as either NAT or route. You can see that mode route here in this return. And on the web, under network interfaces, it gives you that radio button. In order to verify whether the NAT behavior is occurring, you can look in the session table, and you can see here in the session table the IP addresses are not being changed here. They remain the same on both of those lines, whereas in a translated one you can see that the second line of the session here, we've translated the internal address to the interface address on the outbound traffic. The outbound address remains the same, but the source address has been NATed to the 98.111.198.54 address. Okay, directional dependencies. Interface-based NAT is only going to work on sources inside trust and DMZ heading towards trust. So your direction of traffic has to be from trust or DMZ to untrust, not the other way around. So the natting will only occur if the traffic is going in the correct direction. So this brings us to the end of this session on layer 3 operations. What you should understand at the end of this is the need for routing and basic routing operations and how they work. You should understand the virtual router relationships inside ScreenOS and how they relate to each other. You should know how to configure static routes. You should know what the loopback address is and how to create the loopback interfaces and configurations. You should know the difference between route and NAT mode on an interface and how those operations work. And you should be able to verify and troubleshoot layer 3 operations on a ScreenOS device. I thank you very much for your kind attention. If you have any questions on the material covered in this session, you can either post a public question on the forum for the course and interact with anybody and have the question and answer available to anybody, or you can contact me via the course website if you have specific questions on the material we covered here. I thank you very much for your time.